Looking at this first question, we're asked to explain why the angle ABC is 115 degrees. The angle ABC is this one here. We know that the angle AOC is 130. So if we extend these sides like that, the angle at the centre is twice the angle at the edge. So this angle here is 65 degrees. We now have a cyclic quadrilateral created between ABC and this extra point that I've made on the edge of the circle. In a cyclic quadrilateral, opposite angles add up to 180 degrees, so in order to get angle ABC, we take this angle away from 180 degrees, which gives us 115 degrees as required. In order to now find angle OBC, we create a line between O and B. We're told that AB and OB are equal, and given that OB is a radius and OA is a radius, it must also be equal. That means that angle ABO is 60 degrees because this is an equilateral triangle. We know that the whole angle ABC is 115 degrees, so we simply do 115 degrees, take away 60 degrees. That leaves us with 55 degrees as our final answer. In this question, the first thing we are asked to find is angle OQR. Given that OR and OQ are both radius, that means that this is an isosceles triangle, so OQR is 41 degrees. To find PSQ, we use the fact that SQ is a diameter, and the angle subtended by a diameter is always a right angle. So angle P here is 90 degrees. If we know that P is 90 degrees, and we know that Q is 24 degrees, we can find the angle here at S by simply subtracting 114 degrees from 180 degrees. That gives us 66 degrees. Finally, we know that angle SRQ is also a right angle because it's subtended by the diameter. If we know that this portion is 41, then this portion must be 49. And because, again, this will be an isosceles triangle, this portion is also 49. If we know that that is 66 and that that is 49, we simply add them together to get PSR. So we do 66 plus 49 equals 115 degrees. We now have a proof style question. As you know, there are 5 different proofs to learn, and as you can see here, this one is only worth 3 marks. I do not believe that you should stress yourself out trying to learn all of the proofs. They may not come up, and if they do, they will not be a huge amount of marks. whereas the amount of time that it might take you to learn them off by heart could be better spent improving, say, your algebra skills. The proof of the cyclic quadrilateral is a reasonably common one, and it's not too difficult to do. Try and remember the steps that I am doing rather than trying to remember each individual bit of writing. The first thing that I do is I split my quadrilateral by drawing the diagonals into the shape. I then use the theorem that angles subtended by the same chord are equal. So you can see here I'm highlighting the angles subtended by the chord GH. So H, EG, H, FG. If I call those A and A, as they are two equal angles. Now, looking at the chord EH, you can see that this angle EFH and this angle EGH are both subtended by the same chord. So let's call them B. If I turn my shape around, you can now look at this chord FE. We now have this angle FGE and this angle FHE, both being subtended by the same chord. So call them C. Finally, looking at the last chord, FG, we have this angle, GHF and GEF, which are both subtended, and we'll call them D. Once we've done this, it is very simple. Because this is a quadrilateral, all angles add up to 360 degrees. So we simply work our way around the quadrilateral, adding up each letter as we go. So starting here with A and going in a clockwise direction, we have A plus D plus B plus A plus C plus B plus D plus C equals 360 degrees. Summarising what we have 2A plus 2B plus 2C plus 2D equals 360 degrees. Dividing through by 2 gives us A plus B plus C plus D equals 180 degrees. And if we go back to our diagram, we can see that A plus B plus C plus D means X plus Y, opposite angles. Therefore, our proof is complete. In this question, the first angle that we are asked to get is angle OAT. If I draw that line in, going from O to A, you can see that that's a radius. A radius always meets a tangent at 90 degrees. Angle BCD is opposite to angle BAD in a cyclic quadrilateral. Therefore, we take it away from 180 degrees. 180, take away 50, gives us an angle there of 130 degrees. Finally, angle BOD. BOD is this one here. Hopefully you can see that it is the angle at the centre, where that is the angle at the edge. The angle at the centre is always double the angle at the edge. In the first question, we're asked to explain why angle PQR is 90 degrees. We simply have to say here that angles subtended by a diameter are right angles. and that is your answer to the first question. In B, we are asked to get the angle PRQ. Hopefully, you can see that if we turn this around, PRQ has been subtended by the same chord as QSP. Therefore, those angles are equal. So PRQ is also 52 degrees. POQ would be the angle if we drew a line from there to there. That would mean that it was the angle at the centre subtended by the same chord as the angle at the edge. The angle at the centre is double the angle at the edge. This next question is a hard proof. This is the proof of alternate segment theorem. Alternate segment theorem tells us that the angle created between a chord and a tangent is equal to the angle subtended by that chord. In other words, that angle CAT is equal to angle CBA. In order to prove this, we have to use the fact that a radius meets a tangent at 90 degrees. If I call the angle CAT angle A, and that's that whole angle between the chord and the tangent, that means that the angle inside the triangle, angle OAC, is 90 minus A. If I create a triangle by extending the centre O to the corner C, that gives me an isosceles triangle because OA and OC are both radius of the circle. So if the angle OAC is 90 degrees minus alpha, then the angle OCA will also be 90 degrees minus A. Looking now at the angle that we've been asked about, which is this one, hopefully you can see that it is subtended by the same chord as CA. So looking here, subtended by the chord goes to the centre, and subtended by the same chord goes to the edge. We can get the angle COA by doing angles in a triangle, 180 minus 90 minus A minus 90 minus A. So that is angles in a triangle, take away that angle of 90 minus A and that angle of 90 minus A. Because that's the angle at the centre, we know the angle at the edge, which is the one that we want, will be half of that. So we just need to simplify down this expression in order to solve. Simplifying that down, we have 180 minus 90 plus A, because of the double negative, minus 90 plus A. 180, take away 90, leaves you with 0. A plus A leaves you with 2A over 2, giving you an answer of A. If we go back to the original diagram, we said that this angle here, CAT, was A. We've now shown that this angle here, CBA, is also A. Therefore, we have proven that CAT and CBA are equal. The first angle that we're asked to find is A, B, C. So this angle here. We are given angles here and here in this triangle, which means that we can calculate this angle. Because this is then angles on a straight line, we can get this angle. So 43 plus 35, first of all, gives us an angle of 78 degrees. To get this angle, 180 take away 78. So CDE is 180 take away 78, and therefore 102 degrees. Angle CDA, which is this one, is 180 take away that. So in other words, 78 degrees. So CDA is 78 degrees. This is then a cyclic quadrilateral, which means that this angle plus this angle add up to 180. So this angle, which is one we were asked for, is 102 degrees. So final answer, 102 degrees. The next thing that we're asked to find is the obtuse angle AOC. So looking at AOC, we have AOC, we have this angle and this angle. This one is a reflex and this one is an obtuse, so it is the one we are asked to find. It has been subtended by the same arc as CDA and is therefore double the size. Now we said here that CDA was 78 degrees, so COA will be double that size. So that angle will be 156 degrees. In this final question, we refer to the proof that we did earlier, where we did the opposite angles in a cyclic quadrilateral sum to 180 degrees. So you would go through that proof again to show that x plus z are 180 degrees. I'm not going to go through the whole proof again, but you can refer back to the earlier part of the video. Once you've shown that, you simply state that z plus y equals 180 degrees because they are on a straight line, and comparing those equations, if x plus z equals 180 degrees and y plus z equals 180 degrees, x and y are clearly the same thing. So it's enough to simply state, therefore, x is equal to y.